Gary! I was just looking for the sports channel, Gary.
Hey, Millen, good to see you here. It is... Oh, this object does no longer exist. No! I'm loading up our studio. This object does no longer exist. I have to cancel out of it. How you doing today? Let me move. My desk is getting so cluttered. Oh my gosh, why is... There we go. There we go. With that, should we do some 320? Talk about some 320? Talk about what's going on right here? What should we do, Millen? It is your call. You are the one here. So we get to do the work. Hey, Nick, good to see you here. Let us know what should we work on. This mouse trying to get the assignment started early. Awesome. Let's go check out some 320, and it kind of converges to 201. So if you're in 201, here we go. We'll hit don't save. Then we'll load the code from... Let's do a little 320 help right here. 320. Help find data set? Yeah, what are you interested in? Tell me what you're interested in, and we'll help find the data set. So we will find a data set right here. So BAS 320 correlation assignment. Okay, so tell me what you're interested in. You'll pay attention? Yeah. So you need to know what you are interested in. Because then from there, we can figure out what to do. So we're going to go to kaggle.com. Let's do that. There's a website here, Nick. Chess, money, travel. After we talk about some, chapter 6. Tell me what chapter 6 questions you want to do. PC games. Oh, might be PC game stuff. Let's check it out. You've looked at chess stuff, right? Chess positions. I don't know about 4 gigabytes. So the reason I wouldn't, why do you think I'm not going to use this as my analysis thing right here? Gosh, look at that. Why do you think I wouldn't use that one right there, Millen? Chess positions. Why do you think I wouldn't use that one? Why do you think I would not use? It's too big. 4 gigabytes is crazy large. So yeah, not going to use that one. Online chess games, maybe. 1 file, 3 megabytes. That might be good. Okay. Which percent of the games were won by white? How many ended in a draw? All this good stuff right here. Number of turns in a game. Okay, cool. It's a lot of categorical, isn't it? Okay, wait. Oh my gosh. We got enough right here. We got enough, Millen. We can do it. So what do you notice about what graphic is this? So Nick, this goes to 201. What graphic do you see right there? What graphic is on the screen currently? Right there. So there's the hints. That's Black's rating. What do they call it? ESR rating or something? I'm trying to think what they call it. It's a histogram. That's a histogram right there. And then we have the ID of the individuals. That might not be an identifier. It might be a group. There's that many. It's not an identifier because you see there's so many unique values. It's almost an identifier though. So but it's not unique for everyone because how many? 20,000 plus. So there's repeats, and you see it right here at the start. So if we sort it, sort by descending, which it might take a while to do because it's a lot of data. There are repeats. Normal unimodal histogram. Yeah, a little right skew, but I like that. We're some points right there for everyone. Pretty normal, maybe a little bit of right skew. We could actually analyze it. Here, I'll download it. Let's get it. It's gonna actually be quicker probably if we download this. So 2 seconds right here. So this is the one, the online chess games, Millen. Go grab this. I'm gonna call it chess and put it in my downloads. And so we're gonna go there, downloads. We're gonna call it chess.csv. Well, it's already don't call it chess.csv or it'll be chess.csv.csv. So it's now chess. It's in my downloads, and then we're gonna go over here into R. And now that it's in my downloads, all we do is read.csv. A lot of times I'll do this with, I did lowercase chess.csv. There it is right there. And then we'll just call it capital chess because it's data frame. We got the data loaded. So that's how quick, Nick, we can just take data from the internet and get it onto our computer. You can also read tables from online. But now I was using that one, but this one's good. This one's good for your, now we're probably going to do strings as factors. Let's say strings as factors true. And so now we're much better. So we need to look to see if things are quantitative. And we do have multiple quantitatives. You know what we could probably do? We could actually narrow this data set down to only quantitative variables for this. So if we want to see if a column is quantitative, we can do apply. Not that. We want to apply rows, columns. Okay, apply on the chess data frame, fun equals is dot numeric. There go that, and then 2 is dot integer. Same false for everything. Don't like that. What is turns is int? It should say it's integer. Let me see. Chess $ turns. There's the values. Is dot integer. Should say true on that. It is integer. I'm trying to make our lives easier, but I'm just making it tougher because you could just go through here and select the numbers of them. Game ID doesn't matter, but we do have 3 opening moves. That's also interesting. So if we go right here, I'm going to make chess underscore quant or chess quant. So what do you think I'm going to do right here, Millen? I'm going to go right here and I'm going to take, and you can go right here and do the rows columns and do something like this. Turns, and then also opening, oops, I want to put that in quotes, opening moves. Or we could also do it the more traditional way we've been doing stuff with things like, and this is going to actually help, if we store into this and then go here and say select. Oh, no. Oh, you know, what's the problem right now? Why didn't I get select, Millen? Why did I not see select? I don't see select right here. What's the problem with this? Why don't I have select? I want to use select, but I don't have it. It doesn't show up. Yeah, Millen, you got it. The library isn't loaded. A lot of people are like, wait, where's my select? I started a brand new instance of R, so I have to go here and do library dplyr. R. And this is why you want to make sure you only load up the libraries you need. You could get to it by doing this. This is a way to get to the function in the library without actually doing that. It's a bummer because you kind of have to remember what libraries have what after a little while. And sometimes you see things that kind of overlap. So sometimes you have to call the function from the library. So we're going to go here to select. And what's really nice about this is now when we type in turns, it actually shows up right there. So we actually get the autocomplete, which makes it a lot easier. And we can just type in things like that and then have it autocomplete. How's this looking, Millen, right here? So now what we do now is we've now actually made the subset right here of only those quantitative variables. Doesn't matter that they're integer, that's fine. But we have more than enough to analyze. The first variable right here, the game ID, is just an identifier. Although it's quantitative or integer, it's not really a quantity of game ID. It's just letting us know that is. And so 201 right there, Nick, that's an identifier. This is the identifier for the data set. It identifies which game we're talking about. This is a logical true false, which is more categorical in nature. It's like a yes, no variable. Turns are quantitative, and then everything else looks to be categorical with this many answers. Like how did the game end, a draw, a mate. We could go look at that right here by going to chess, or really quick, we can look at table and chess, and we could go to victor status, and we can see the percent of times. A lot of people resigned right there. So that's pretty interesting. That's, you know, when people, I guess when you get towards the end and you just resign the game. So, but that's not really related to this week's assignment, but good to know and good to be able to analyze. What's even better is we can put this in a quick plot, and this is not this week's assignment, figure too large for margins, and we can make a box plot pretty quickly. Now that's a horrific box plot. So Millen, how are we going to make better graphics? So that we don't want to turn this in right here. This is no. That is what, yeah. And so we don't want to turn in this stuff right here. How are we going to make this better? What options? Because if we turn this in, someone's going to be like, GG, the GG plots. So GG plots stand for the grammar of graphics. And I think ggpubr will load up ggplot. There it is. So it's loading a required package because, so it did the work for you of loading ggplot2. ggplot2 is already loaded by doing ggpubr. And then we're going to make our lives easier by going to ggeasy, which has a lot of easy functions that make using ggplots easier. So ggpubr, I think it's like publishing in R. That's the way I think of ggpubr. Makes graphics a lot nicer. So when we go to gg bar chart, this would be a bar chart right here. This is a gg bar chart. It says it needs a data, it needs an X and a Y. Now we should just be able to enter in the data, chess, and then Y equals, I'm going to have to look at how it is written, but it has to be in quotes. We're going to put this on a separate line to make it all pretty right here. And it's showing up. Going to show up. Oh my gosh. We can't turn that in. So I think it actually wants the counts, which I always dislike about the ggbar plots and stuff. Let me see how it wants the data. Okay, so if your graphic looks weird, you always go down to the help right here. And so it's actually doing the counts of the observations. So it's taking a table, and they're taking a data frame right there. So where's in a really easy format? ggbar plot of those. Hey, Jesse, good to see you here. And so we'll talk more about this week in a second. So they're making a data frame of these values right here from, so they have a data frame of those values. And so what we would need is that vector we just created right here from the table. We need the names of the table, which are going to be the first thing. There's the names, and we'll call this names. And then we'll store the names into outcomes. And those are just the names right there. And then we'll take the values and store them as .numeric. And what this is going to do is this is just going to store the values right here from the table. And then we'll just put the outcomes, and we'll put count right here of that. And then ggbar plot, or we're just now going to copy their format right here that they already have, where we have data frame, and then we have outcomes. I'm going to give it a capital, and trying to think what the order is. Okay, the dose goes first, so that's that, and this goes here. We should get an object closure. Dun, dun, dun. Oh, wait. Oh, something's wrong with that. What are you thinking, Millen? Oh, did I? Because outcomes, did I mislabel? Names. Oh my gosh, look at this. Names not found. Oh my gosh. It's always capitalization. There we go. There we go. Should be easy enough to go here and go to fill, and fill equals outcomes. Should do it. There we go. And then legend equals right. And, oh, didn't go to the right, just deleted it. But case sensitive, exactly. Or is it lowercase for this? There it is. Oh, look at that. And then we go here to plus, easy. Or we could do labs first, labs, and say labs title equals outcome of chess games. And then x equals lowercase x equals outcome of game. And then y equals count of observations. And what's it mad about? Oh, I put a, there we go. One little thing, and then plus, easy. So the whole point of this is how much nicer does this look, which I think, Millen, you know all about. How much nicer did we get this to look? And it's slightly off the screen, which I'm mad about. We might need to go here to, I think it's scale y-axis, no, what is it, y-lim 0, no, concatenate vector 0, comma, I should take both, right, 0, comma, there we go. What's it mad about? Removed one row. Excellent. No, it's getting mad at me. Dun, dun, dun. I don't like that it's slightly off the scale. You do the exporting? Yeah. So export, save as image. See, it's slight. That would drive me crazy. And we should be able, you know what I could do? Watch this. Save into P, and then library, plotly. And we're going to do just a little bit more on this, Millen, because, and then I'm going to have to not work with your data set here. I'm just kind of showing what's possible with making graphics right now. And let's go here to ggplotly and do this. And now, oh, the numbers are, I don't like where the numbers are at. That's a little better. And we could export, save image. So we could export this image. The labels are a little bit on top of it. I might even remove those labels. So label false. I don't know. Sure, why not? I don't know. It's we could fix it up and then scale it. Yeah. So you can do all sorts of things. And this is now an interactive graphic, which is really neat. So let's talk a little bit about this week's assignment right here. So you can use this data set. I don't want to do this week's assignment with your data set, but I want to show kind of what we're doing with this week's assignment. So I'm going to pull up some data here from reg class. So I have to load up reg class, then I get access to survey 10, which is inside of reg class. This is a data set that is kind of preloaded into R. And now survey 10, as we can see, let me clear everything out. Survey 10 right here has quantitative variables. Quantitative variables are going to be the numeric and integer ones, and we can do some quantitative analysis right here with things like height and weight, or weight and desired weight. Now, we put some code on the Discord already, so go to the Discord. It's the pinned message right now, so you can go to the pinned messages on Discord, grab all this code right here, and just drop it in. Now, if you notice, this code looks like a lot. Are we going to have to change a lot of this code right now, Millen? Are we going to have to change a lot of this code? Are we going to have to change a lot of this? Are we going to have to change a lot of this? Yeah, chapter 6, you bet. Mention which ones, and we'll start doing some chapter 6 real soon here. No. What do you think's the main thing we're going to have to change if we're making a plot? Really, we don't have to change that much. Yeah, chapter 5. So let me put the start of each question in here, like the steers and percentile, put the very start of it. I'll start marking it over here in the notes. So just tell me the start of the question you're looking at, and we'll be doing about 5-10 minutes, I bet. The names of the variables, exactly. So we are using survey 10 data frame. We want to do weight, and we want to do height. So does weight explain height? And then also correlation between weight and height. And I think, is that it? Oh, and then here we go right here. Weight is the X. And this is chapter 6 for 201. And now if we run everything, if I haven't done anything wrong, geom smooth right there. Oh, and then are we not doing it? There we go. The label is a little bit too low, but we should notice something immediately. And 201 should notice this too. What issue is there with this graphic? What issue is there with this relationship? Yeah, good answers. So what issues, does anyone notice an issue with that or with this over here? There's two issues. And so 201, this is very important for chapter 6, which we just covered. There's two issues. There are two issues. There's an issue here, there's an issue here, and issue here. So that's kind of like issue 1 and issue 2. Outliers. So issue 1 is outliers. There are things that are far away from the relationship. And issue 2 is kind of like this. So how would you describe issue number 2? Issue number 2 is what? So there are some outliers which can do anything to correlation. We don't like outliers. The correlation is 0.6. It is statistically significant with a p-value well below 0 or below 0.05. The p-value down here is basically 0. It has a little bit of heteroscedasticity. Heteroscedasticity is plot thickening. We might even mention that today in 201 because we're going to cover a little bit of chapter 7 and talk about how it relates to chapter 6. There's a tiny bit of heteroscedasticity, but also more importantly, I see this right here, Millen. I see that. So heteroscedasticity, some. Outliers, some. I also see some what? Very importantly, I'm pointing to this right here. What is monotonic? It is monotonic. Why is it monotonic? It is monotonic. Monotonic means goes in one direction. So it is monotonic. It's pretty monotonic. But it doesn't look to be completely what? It doesn't look to be completely what? It is monotonic, but it doesn't look, it looks to be a little non-linear. So Pearson, we have two choices of correlation. We have Pearson, which we learn in Stats 101, and we have Spearman. The only requirement for Spearman is that it must be a what relationship? The only requirement for Spearman is that it must be a what relationship? The only requirement for Spearman correlation, rank-based correlation, is that it must be a what relationship? These are the theory. Yeah, and technically, yeah, you are correct. Two quantitative variables, that's where we do correlation. So that's a requirement for any correlation. Good job right there, Millen. And then monotonic. So any correlation must be quantitative. And then Spearman must be monotonic, which means goes in one direction. So what are the last two conditions for correlation? From 201, What are the last two conditions? QQ, something, 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 something. What are the last two conditions for Pearson, which Spearman does not have? What are the last two conditions for Pearson, which are not required of Spearman? You can have those. You can have those issues with Spearman. Straight enough, no outliers. So guess what, Spearman?
It doesn't matter.
Spearman's fine with those. Spearman's like, sure, I can deal with outliers. I can deal with things that are not straight enough. If this has outliers, fine. If it's not straight enough, fine. But it has to be monotonic, and you have to have two quantitative variables. So here's what we're going to change. This is what you have to change right here. So take note if you're watching this for 201, and for 320, is we're going to go right here and change the regression line, which is the line right there, to the local regression. Local regression does regression over each like part. It does a local regression just to the area. You'll see what that looks like here in a moment. And then when we go to the method, we're going to change this to Spearman. So the method is now Spearman correlation, and then we have local regression right there. So now when we take a look at this, we'll rerun everything here, the plot looks very different. And we really see that bend at the end of it. So if you notice, there is sort of a bend here, and that one outlier, I wouldn't say it's really a change in the relationship, but there is a bend as you go through the plot. It starts to level out right there. So this is better described by a Spearman. This is much better described by a Spearman relationship. Is that making sense, Millen, right here? So this is better described by a Spearman, and I would definitely talk about these values right here. Now you could run the associate function to get the graphics. I'll also be probably sending these out tomorrow. We go here to height as the Y, weight as the X, data equals, survey 10, and now we get the association graphics down here. So you could take screenshots of these. What are you wondering about, Millen? Well, tell me what you're wondering about, because I can help explain that. Let me know your thoughts. Let me know your thoughts. And this down here on the bottom would be if we took X and Y. So X needs to be a sample of survey 10 $ height. That's the Y. That's the X. And then the Y needs to be height. And then we need to go here and take the core.test of Y comma X. And is it core? No. 2 seconds. I'm going to find this. No. Statistic. No, we don't want the T. Estimate. There it is. Okay. And then as dot numeric. I was wondering how about to understand the monotonic since you said it levels out. So why would it still be monotonic since it doesn't really go back down though, does it? Does it really? Let's look at the graphic again. Monotonic means goes in one direction. So, and think of it, is it generally monotonic? So you want to look at this plot and you want to ask for monotonic. Let's look at 10 points on this plot. So tell me at any point on the plot, is it generally going up? Now I see it goes a little bit down right there. But does this plot generally go up? Monotonic doesn't mean it has to go up 100% of the time, but does this generally have an upward direction? Like, could it be well described by something like that? Like, does that look like it, or does this look more like it? The one on the far left is non-monotonic. It generally is monotonic. So remember, we're not looking for perfect with these things. We're looking for generally monotonic. So it's pretty monotonic. You wouldn't say it's perfect monotonic. And so good points right there, Millen. You wouldn't say it's perfect monotonic. You would say it's kind of monotonic. So is it pretty monotonic? Because nothing's perfect linear. That's why we say straight enough. We could say monotonic enough. This is monotonic enough. QQ, straight enough. No outliers. So QQ, monotonic enough. Anything else doesn't matter. So it's generally monotonic right there. Pretty monotonic. Pretty good right there. Yeah, tell me if we assume the conditions are met. Yep, I've got that marked. So drop a few other questions here and we'll get started here in a second. I'm putting that in the notes. And yep, we'll do that one here next. I'm going to see if I can get this graphic made really quick, and then we'll post it on the Discord too. So there's one round of that. There's the numeric. Let me say here value again, and then value sub I. And we want to go right here and say 4. I in 1 through perm equals 500. Oh, there we go. I got it. There. Oh, wait. Should have all the values. We're going to store the value to start, though. Should be writing it. List of 500. No, we don't want the list. As.numeric should be taking just that estimate. Oh, because I'm overwriting the value. Val. I see what I did. There we go. Okay. There we go. Okay. GG hist. So this is... Yeah, Nick, you got it. GG histogram. And now we have to turn this into a data frame. df right here, data.frame of the value. And df, comma, value. Do we still have that code? Oh my gosh, what have I done? No, this is the weirdest thing I've seen. Wow, that was weird. Oh, is it? Oh, y equals... Oh, it's mad. It's mad. It's always mad. Oh, values. Look at that. Okay. Still mad. Still mad. Here, we'll put 2 minutes on the clock, see if I can get this fixed up. Where is that first graphic I made, Millen? The first graphic I made with the permutations. So I need that code. I'm going to have to go find it really quick right here. And... permutation. Okay. I see a bunch of... Where is it? Going back. Oh, I need to go back further. Let's see if I can get this. No. GG histogram. I know I made the GG histogram. Where did I make the GG histogram? GG histogram. Okay, here we go. GG histogram. My histogram. Count GG. No. Where is it? And I'm also wondering why this wouldn't be... Oh, it's lowercase df. I call it lowercase df. And the GG histogram should be making. Let's go look at the way GG histogram is made right here. And here's GG histogram. Oh, it's x equals... I should be able to make this pretty quickly. Okay, and we don't need the mean. The rug is fine. So now what we want to do is we want to add in where R observed is. So watch this. We're going to go to add to this geom. What is it? We want a vertical line. Geom V line. So geom V line. And then geom V line, right? Vertical line. And geom V line. You have to put the positions of it. I thought I used this previously. I thought I did. Are you? Yeah, we're remaking that graphic here. I'm going to take just a few more minutes on this. I thought it was GMV line. Add vertical line. Add vertical line to ggplot2. Here we go. Literally the web page now. So it's geom underscore. What is that from? So geom underscore v line right there. That's it right there. And it's x-intercept. X-intercept equals, let's say 0.8, just for the moment. Col equals red. And there it is right there, but that's not the value of our correlation. So we need to go right here and do core.test on the survey 10 $height, survey 10 $weight. And then we need the value of the estimate, which is right here. And then we'll store this to our value, and that's our value. So then we go right here, do that. There's our value. Then we add another line, and we can make it a dashed line, and we go right here, and we take our estimate, and we times it by -1. There's the other line. We're going to make that a dashed line now. Line type dashed. So we add in another argument right here, and we go and say line type dashed. There's the other one. And we actually have no, we don't have the p-value being calculated right here, Millen. But yeah, you're right, Millen, it'd be geom line. And then we can add titles to this. We can make it look nicer, because all we're going to do right here is say like plus labs and then say title. And we could say our observed correlation to permutations, whatever you want to call it. There's the title. And then we could put the x equals random permutations, because that's what those are. And then we could also graph the p-value, but can you tell what the p-value is by looking at this, Millen? Can you tell what the p-value is of this by looking at it? Why is there so much space between the histogram and the exact? Well, so this is our observed correlation. Correlations by random chance are usually close to what? Correlations, so well, our observed correlation is 0.6, right? And one just as extreme is -0.6. The observed or the random permutations are close to 0. So are any of the random permutations more extreme than ours? Are any of the random permutations more extreme than ours? Are any of the random permutations more extreme than ours? So what would the p-value be when we run the test on this? If I go here and run the test again, what would the p-value be on the test? The p-value is basically going to be what? It'll be 0. The p-value is basically 0, because the p-value is the area shaded outside the probability of a result just as extreme as ours, and there are no results as extreme. So if we did random variables, we'd land closer to the center right here, but our correlation is so extreme that none of the random correlations are as extreme as ours. So the p-value is basically 0. Does that make sense, Millen? The p-value is basically 0. And this is, like I said, I don't, so does that make more sense when we do the permutations? These are the ones created by random chance. This is our observed result, our observed correlation, because our correlation is 0.6. Here it is right there. There's the 0.6. This is one just as extreme, but negative. It's just as strong. Exactly. So in this instance, it's both sides of it, because a correlation just as strong as it would be -0.6. So a correlation just as strong would be -0.6. Well, good work right there. Let's head over here. We'll do some 201. Okay. Time for some 201. 201 time. Chapter 6, here are several scatterplots. Yeah. Okay, let's take a look right here. If we assume the conditions. Here are several scatter plots. Let's take a look. Okay, so when we look at correlation, the stronger the correlation is, the more it'll look like a what? So when correlation is stronger, what are the highest values of correlation? What are the highest values of correlation? Like the strongest, we should say. What are the strongest values of correlation? What are the strongest values of correlation? 1 and -1. So when correlation is weak, it'll look pretty random. And this one right here does look pretty random right here. So this is the weakest correlation. And the weakest value of correlation is 0. So right here, this first one, A, is going to have the weakest closest to 0. Now you have to be careful. Let's look at the direction right here. B goes in what direction? B goes in what direction? So what direction does B go in? What direction does B go in? We're just looking at the direction right now. It's negative. Is it weak or strong? So B has a negative direction. Is it weak or strong? B has it's weak. So we need negative weak right here. So negative weak is going to be this one right here. And then this one is stronger and positive. So right here, we need stronger positive, and then we need very strong negative right there. And that's got it. There we go. Good stuff. Good question. Good one to work through and see how to do it. Excellent stuff right there. Okay, let's look at the next one right here. If we assume the conditions are met. Here's more several scatter plots. So this one, very similar right here, but the first one up on the top left actually shows, is there one with a parabola? Yeah. So a parabola has a correlation close to what? A parabola has a correlation close to what? So a parabola would have a correlation close to what? Is it a linear relationship is the big question to ask. A parabola would have a correlation close to what? 0. So we need to find the correlation closest to 0 for the parabola, and 0.006. Now we can look at the other ones and do the same sort of thing. This is negative, this is positive, and this is very strong negative. So C is the strongest negative right here with negative 0.977. And then D is positive 0.777, I believe. And then B is also negative right here, negative 0.487. And that should do it. So really good questions, seeing if wouldn't be close to 0. That is correct, because it doesn't have any linear correlation. Remember, correlation only measures linear strength. That is what correlation measures. So good stuff right there. Really good questions. And let's take a look. If we assume that the conditions, if we assume the conditions there we go. If we assume the conditions are met, let's mark this question. 4013. Oh, brackets aren't allowed. Stat 201, chapter 6, quiz. Okay, if we assume the conditions are met, which of the following are true? A correlation of 0.02 indicates a strong positive association. What would a correlation of 0.02 tell us? What would a correlation of 0.02 tell us? So a correlation of 0.02 would mean it's what? Don't read their answers. Always think about what it means. A correlation of 0.02 means what? The correlation, the linear correlation is very what? A correlation of 0.02 would mean what? What would a correlation of 0.02 mean? That it's very, very what? What would a correlation of 0.02 mean? .02 means it's very, very weak. So a correlation of 0.02 indicates that there may be no linear association, and that looks right. That would be right there. It's not linear. So 0.02, that means it's close to 0, no linear association. Standardizing the variables will do what to correlation? What will standardizing variables do to correlation? And we really need the notes open for this one, so I'm going to go get the notes. Standardizing the variables will do what to correlation? So what does standardizing the variables do to correlation? What does standardizing the variables? All the notes are about to pop open on my computer right here. Standardizing the variables does what to correlation? What does standardizing variables? It's literally trying to open all the notes. What does standardizing the variables do to correlation? Any thoughts? So the notes show us what happens. In the notes, we have the equation, and the equation is right. Where's the equation? Here's the equation. So there's the equation right here. We already turned them into z-scores. Z-scores standardize variables. So we're already standardizing the variables. So what does, if we standardize them again, what will that do to the correlation? So correlation is already standardized. So standardizing it does what to correlation? Z-scores are standardized metrics. So correlation is already standardized. It's already unitless. So what would standardizing it do to it? Absolutely nothing. It's already standardized, so it's not going to do anything. So the value of correlation, billion slides right here, the value of correlation would not change. Standardizing the variables will, the statement is false. Change the units of both of the variables, or in this case, removing the units by standardizing will not affect it at all. That is the case right there. It does not change it. Adding an outlier can dramatically change correlation. That is just a fact. That's why we say QQ straight enough, no outliers. That is a fact right there. What do we say right here? There may be no linear, and that should do it. So really good question. Make sure you know the theory on these, though. Make sure you know all the theory on why these things apply. Once again, you should be able to explain, like standardizing the variables right here. You can see it in the equation that we already turned them into z-scores. So correlation is already a standardized metric. So it's not going to affect correlation to standardize it. Then you can also see when we talk about a correlation close to 0, that means there is no linear relationship. We did lots of examples right here throughout the notes where we talked about correlation could be close to 0 and it would have a non-linear relationship. We also saw that a second ago. Last but not least, we have an outlier, and outliers can do anything to correlation, and we've seen that way throughout the notes that we say QQ straight enough, no outliers. What other questions are there? We're done on questions right now. Let me know your questions. Which ones are you thinking about right here? Give all the questions. What questions do we have? As the test approaches, what are we wondering about? What questions should we work on? Yeah, Harrison, which one do you want to do? Question, content, part 1 if we assume the conditions are met. Let me know which one, Harrison, right there. Tell me which one to do, and we can do that. Wait, do we assume the conditions are met? Chapter 6 homework? Okay. Chapter 6 homework. Okay, let's go check out the homework version of this. Homework time. Be right back. Right back. We're back. Okay, let's go grab that homework assignment. Okay. Okay, we have the assuming the conditions are true. Got a lot of questions in the chat now. I like it. Okay. Assuming the conditions are true. We'll grab the timestamp on that. And let's go check it out. Okay. So if we assume the conditions are met for correlation, which of the following are true? Briefly explain. So here we are. A correlation of negative 0.98 indicates a strong negative association. Okay, so how do we know this is negative? How do we know this is negative? How would we know that this is negative right here? I know it's kind of an obvious question, but we do need to know these things. Like, how would we know it's negative? We'd know it's negative because it's negative, the negative sign. And then strong means what? If you say something is a strong correlation, it is closer to what or what? So if we say something is strong, it's closer to what or what? Closer to -1 is correct for negative strong or -1 or 1. Exactly right. Great job, Nick, right there. So 0 is the weakest, and so that is a very strong negative correlation. So with this right here, next we see multiplying every value by 2 will double correlation. Well, this is a great question to think about theoretically. So what is the highest value of correlation possible? What is like the highest value of correlation? You could say highest or strongest because there's two strongest, but what is the highest value of correlation? What is the highest value of correlation? So think that over here. The highest value of correlation is what? Like in terms of numeric, like biggest number. The highest value of correlation would be what? It'd be 1. So if we were to double the correlation, then what would the correlation be if we had a correlation? We multiply everything by 2. So here's the correlation between these numbers, which has the highest correlation. It has a correlation of 1. So theoretically, if it's true, the correlation should be what? Like, what would the correlation be if it were to double? So basically, I'm asking you, if you double it, what would you get? So if the highest correlation is 1, you'd get 2. So what's wrong about that, Skylar? It would still be 1, so this is wrong, right? If you double correlation, or if you double the values, it won't change the correlation. We could make it so it's not perfect. We could make it not perfectly correlated. Now it's 0.79, and if you don't double them, it does that. Because here's the thing, when you do correlation, everything is turned into what's again. When you do correlation, everything is turned into what's. Everything is standardized and turned into what's. Z-scores. So it doesn't matter if you double it, it's not going to change the correlation. So that's kind of what this question is getting at right here. It's not going to matter. So do they say the Z-score? It will not change. I mean, that's literally, it doesn't change it. The units of the correlation are the same as the units of Y. Correlation is what in what units? Or we'd rather say it's this unit or unit something. Correlation is a standardized metric. So what will we say about its units? When it comes to correlation, what are the correlation units? Because it's in Z-scores, and that's why the last one worked out so perfectly. When it comes to correlation, correlation is what? It doesn't have any. It's unitless. So we go over here, and correlation has no units. It's unitless. A really good question right there. Which is following? It tells us which of the values. Wait, what is correlation? Is the measure strength and direction of linear relationships? That sounds right. It's not all. Yep, that's what it measures. Which of the following is true about correlation coefficient? We should always calculate the correlation. No, well then it's this one. There we go. I mean, once I read the first two, I was like, well, it has to be the last one. We should only find correlation between two variables if they are quantitative, straight enough, and they have no outliers. So QQ, straight enough, no outliers right there. So think about the concepts we're learning that you should know the conditions for correlation, like two quantitative variables, straight enough relationship, and there are no outliers. So that is literally the QQ, straight enough, no outliers. Also, the saying correlation proves causation is a falsehood. We should always calculate the correlation between two quantitative variables. No, you should always start by making a what between two quantitative variables. You should always start by making a what between two quantitative variables. You should always start by making a what between two quantitative variables. Always start by making a what, which we were doing earlier. If you were checking out 320 earlier, well, there's some right there. We were doing it for 320 over here. Millen and I were working on some stuff. Scatterplot, yep. So we made some really good scatter plots where we were looking at the linear / not linear relationship. I think it was right here. There's the bar plot we did over here then. So here is where we were looking at a slightly nonlinear relationship. And this has outliers down here. This is actually, I'm going to change it back to the Pearson coefficient. So this is a Pearson relationship now, and I'm going to add in the regression line, which is the straight line. And we can see right here, even better yet, and I'm going to do this really quickly. So let me copy, watch this. We're going to take this code, move everything below here, because we don't want that anymore. We still want that, because I'm going to use it later. Don't want to delete what I'm going to use. We're going to make some space. And we're going to do a new question here in a moment. But we are going to copy this, reverse time, good, and then go here, do this, call this SP2, and then do the following. No, we don't want to. I'm going to go here, SP. There we go. That's SP2. And then store this into SP. And now, good. And now we go here and we go library patchwork. And then we go SP plus SP2. And we could work with this a little bit here. There's our two graphics right here with the Pearson and Spearman relationships. I'd probably change these, but now we can see the linear versus the monotonic relationship. And this is the concept we cover in 201, which is Pearson's R. And then this is Spearman, which is picking up on it a little bit more. So there's a little bit stronger of a Spearman relationship here. And we see the local regression, which gives us more of an idea of the monotonic. So it kind of went back to a little 320 right here, but also we're making a scatter plot, making our graphic look nice. And I'd probably just change the titles right here to say Spearman correlation and Pearson correlation. And yeah, that's the kind of graphs we're looking for in 320. And that's the kind of stuff we do, make some really beautiful scatter plots. So we got some other questions. Let's go check them out. Okay, I think someone said, which of the following is a property of correlation coefficient? Okay, let's do more chapter 6 right here. Which is a property of the correlation? So that's chapter 6 quiz, is it? And then people said some chapter 5. Or so we did that one. There was chapter 5 questions, right? I thought I saw some chapter 5. Steers and percentiles, Skylar wants. Okay. Thank you, Skylar. Let's do this. Let's do the which of the following is property? Okay. Chapter 6 quiz. And here we go. Which of the following is a property? Probably towards the end. All these questions right down here are usually at the end. Which of the following are properties, right? Oh, which of the following are properties of correlation? So it's always between -1 and 1, including those values, true or false. It's always between -1 and 1. Is that the range of correlation? Very true. Good to see her, Sloan. Let's sort some points out. That is true. So it says if you use X and Y and Y and X, so you see how here the correlation of X and Y. And if I do the correlation of Y and X, is this value of correlation right here the same as this value of correlation right there? I have different X and Ys, I think, now. Are those values of correlations the same? So I just did the value of correlation between X and Y and the value of correlation between Y and X. Are those the same? So it's like if you take, let's do $.sign estimate right here. Are those the same? Yes, sir. So the correlation values are the same when you do it with X and Y, when you flip-flop them. So it really doesn't matter.
It doesn't matter
Which way you do the relationship. It's the relationship X and Y have. So if you say X explains Y or Y explains X, well, we usually like to say X explains Y. So it's going to be the same. The sign of the correlation tells us the direction. Does the sign of the correlation tell you the direction of the correlation? Does the sign of the correlation tell you the direction? Very true. Very, very true. The correlation is not affected by changes in units and scales. Why would correlation not be affected by like doubling it or measuring it in inches or miles? Why would correlation not be affected by changes in units and scale? Why would correlation not be affected by it? I'm looking for my one. There it is right there. Why would it not be affected by changes in units and scale? And the answer is right here. We won't solve this equation, but the answer is in the theory behind this. Correlation is not affected by changes in units and scale because whenever we do correlation, the formula right here turns it into what's, which are going to be unitless. It's z-scores. So it doesn't matter if we do it in miles or in inches. It's still just standardized units right here. So you could, like, for example, if I were to go here and collect heights, and we collect height in inches. So 75, 72, 60, 54. And then we go here to height in feet, which would be taking the heights and dividing it by 12, and then we can see how tall someone is in terms of feet. So let's go here and turn this into z-scores. The first one as z-scores is the following. So there's the z-scores of the first one, and then the z-scores of the second one are what? So look at the z-scores here for the first individual and the first individual, and this is for the heights in inches, and this is for the height in feet. The z-scores are the what? So this was height in inches, and there's the z-scores for the people. And then here's the height in feet, and there's the z-scores. So the z-scores are what for these individuals? The z-scores are exactly the what? They're the exact same. Because when you turn things into z-scores, it's how far are you away from the mean. So it's not going to matter on the units of the problem, at least if we measure in feet or in inches or in miles or in centimeters. The z-scores do not change because it doesn't matter really how you measure the variable. It's going to, as long as you do it correctly. Now, make sure you correctly measure. He's working. He's there. Ubot's there. So that is very true also. We can do some steers and percentiles. Problem is, a lot of times when people do these questions, they might just check every box and be like, oh, the answer is every box. But you have to know these concepts like, what would -1 look like as a correlation? So what would -1, if I were to draw a correlation of -1, how would that look? So who can tell me in the chat how a correlation of -1 would look? So this is what you want to be able to do if you're working these problems. If I said draw a correlation of -1, I like to take a moment extra on these questions to make sure people understand them, because we don't just want to click every button and be like, okay, the answer is check all the boxes. Then you haven't learned anything. Oh, Mubot's not working? Holy mackerel, he hasn't been here this whole time. Oh my gosh, I've been clicking the points button? Let me throw out some points again. I'm waking him up right here in the background. Yeah, sorry, Mubot was asleep there that whole time. He's waking up now. He's waking up. There he goes. Sorry about that. Didn't wake up Mubot. I'm glad someone noticed. Let's throw out 100 points for noticing. Now Mubot's awake. It'd be a straight line pointing down. Correct, Jesse. So if it is -1 correlation, then it's going to be that we have a straight line and every point is on the line. What about if the correlation is 0? If the correlation is 0, so if it's -1, it's perfect. Everything is on the line. If the correlation is 0, then what would the correlation of 0 look like? What would a correlation of 0 look like? What would a correlation of 0 look like? Which is the weakest linear correlation. A correlation of 0 would look like what? What does a correlation of 0 look like? Gotta throw out more points. Anyone know? A bunch of dots everywhere. Exactly. Or what? There's other ideas. You could say it could also be a correlation that is not well described by a what? Many things. Could be a parabola, right? Because a parabola is a blank relationship that is not blank. Finish my sentence right here or complete the things. A parabola is, this parabolic relationship is very blank, but it's not blank. But it doesn't indicate no relationship. This parabola is a very blank relationship, but it's not blank. It's a very, very what relationship? So the parabola, strong but not linear. Exactly. So remember, correlation only measures linear strength. So if you were to put a line through this, it wouldn't be very linearly strong. So this is very strong but not linear. So remember, whenever we say correlation is 0, that means there's no linear relationship because we have QQ straight enough and the straight enough component. Now in tool 1, we only use Pearson. And what's really cool, Millen, if you didn't see it, we just did this a moment ago. We made 2 plots right here. I'm using the patchwork library to connect the plots. And then I could relabel these like correlation Spearman, correlation Pearson. And you can see right here the slight nonlinearity that we're talking about, still mostly monotonic. And that goes into 320 where we talk about we have ways of handling outliers and nonlinear relationships. And this is the local regression. Yeah. So I would just relabel these plots. And then you've got a really good example showing like your Pearson versus your Spearman and doing the comparison right here of the values. Like here's the Pearson R and here's the Spearman correlation, which is a little bit stronger. And that was just done by, rewind the video a little bit, you'll see me doing it. I just duplicated the code, stored it, and then did the library patchwork. We don't generally go by that. So really good question on that. We generally, yes, if R is higher for Spearman, it probably means it's better or stronger, because higher meaning like more extreme on the -1, +1 side. But remember, you want to use it when there's outliers, when it's heteroscedastic, when it's not straight enough, but it's still monotonic. So that's what you want to explain to the reader why you're doing it. So you wouldn't just say, like, a bad explanation is Spearman is higher, I use Spearman. A good explanation is there is nonlinearity, especially at the end. It's mostly monotonic. The one outlier at the very start might be pulling it up, but there are other outliers throughout the plot at the very bottom right. And at the top left, there are outliers. So due to the outliers, small amounts of heteroscedasticity where the plot's getting maybe a little bit thicker throughout, and also the nonlinear relationship, we are going with Spearman. This is also seen as a good choice because the Spearman value is a stronger value at 0.67 compared to the Pearson of 0.6. Does that make sense, kind of what to say, Millen, for your report? Like you're trying to communicate these concepts and the idea between Pearson and Spearman, when to use Pearson, when to use Spearman, like what they mean, what these values mean, that they're statistically significant, that we think the relationship between these variables is unlikely by random chance. I would also square it and talk about the R squared right here. So 36% of the variation, or about 45% of the variation, is explained by the rank. 45% of the variation in the ranks. So if you need help explaining anything, let me know, but very important to make sure to explain things properly. I think we're gonna do the steers question here. I love the advanced stuff. I love, in 320, we really get into explaining stuff. 320 is all about communicating topics. So we really want in 320 that you know how to talk about this stuff. You know how to, if someone said to you, what does this correlation mean? What are you finding? What's the point of this? You'd be able to explain it to them. We don't want in 320 for you to be like, I have no idea what I'm doing. I'm just putting code in and getting values. I just need to get the graphs situated. Yeah. Yep. Let me know how you're working with the graphs. We're going to do some steer weights. Oh, we have NFL one too. Someone mentioned NFL. We'll do the NFL. We'll know steer weights or NFL. You'll mention steer weights and NFL. Steer weights and NFL. Got percentiles on the steers. Yeah, they're very good. They're very good. They are very good reviews. Very, very good reviews. Let's do the steer weights right here. And nice checking out. Oh, which is a fine property? Let me take a guess at this. Okay. Okay. The steers, the percentiles, not the percents. Yep, the percentiles. Uh-huh. So let's check this out, and here we go. So whenever we get a question like this, let's first mark the time right here, 1:08. Whenever we get a question like this, what should we do? What should we do? We have some very important steps that we always do with questions like this. Very important steps. We always do them. Find the mean standard deviation. We do use the applets, but we're also going to draw it out. So this is where the real practice comes into play. And you want to be able to draw these things out and understand what you're supposed to look at. I had a question about the test. I have worked with the lockdown browser in the past. If I lock down to simply write out a problem, will it flag me if I look down? No, it shouldn't. No, we're very careful about who we report for cheating. If you're looking down, it shouldn't do it. Just make sure you're not like looking down. And I've only reported one student ever for cheating. And let's just say they were pointing at stuff and whispering. And you could also tell someone else was in the room. Let's just say the video showed some pretty concrete evidence that it wasn't just me thinking they cheated. So it was pretty bad. If you watch, you can't watch the video, but let's just say they didn't realize that they accidentally caught their person that they were with in the video a few times. So yeah, exactly. We're very careful on who we accuse of cheating. We take each accusation super serious. And we are going to make sure if we say anything to you, we come with very, very big evidence. We don't like it. It's not fun. It's the least fun part of my job. So I don't like it. So we are drawing this out right here. Please do this. This is the best way to learn these concepts. And we are going to take guesses. So we're doing this the way of taking guesses. And this is normally distributed with a mean of 1161 with a standard deviation of 61, was it? There it is right there. You're welcome. You're getting an error. Message me on the Discord, Millen, and we will get that fixed. So how did I find that number right there? How did I find this number right there? How did I find 1,101? How did I find 1,101? How did I get that number? Why did I type that number right there? Oh, wait a minute. Oh, good. It's one standard deviation below the mean, exactly. So these are the z-scores. Mark your z-scores on the curve always. And then always, and please, I feel like too few people do this. There we go. So one. Like this is the best way to learn this and to practice it. Then you know what you'll be looking for. It'll make more sense on the test when you're like, let me look at the graphic. If I can draw it out. Just take a moment right here. It becomes second nature. And then before you know it, you're like, okay, that makes sense. I know where I'm at on the curve. The normal curve, I know what these values represent, that this is at 3 standard deviations above the mean. Okay. Now the 40th percentile. Well, let's mark some percentiles on the curve. Right here is the what percentile on the curve. Right there is the what percentile on the curve. What percentile is that at if you're at the mean on the curve? What percentile? The 50th. So where would the 40th percentile be on this curve? So the 50th is right here because that's the middle of the curve. Where would the 40th percentile be on the curve? So percentile means the area below you. So where would the 40th be? Well, not quite one. So one standard deviation below the mean would be where? So if we go one standard deviation below the mean, what percentile is that at? That's a good question right there. So if we go one standard deviation below the mean, what percentile is that? So let's find that right here, and then that will help us. And Skylar, you are correct. Well, careful, Skylar, or maybe we'll see here in a moment. So remember, percentile is area below you. Like what percent of observations are below you? So what percentile is this right here? What percentile is that? That is the what percentile right there. So we're asking what percent of data is below there. That's what it means to be a percentile. What percent of observations are below there? So that's what percentile means. What percent of observations are below there? Close, Millen. Very close, Millen. And Skylar, that is correct. So the answer is 16%. And that's found by... Oops, that doesn't look like a 16. 32 on the outside, 16 on either side. That is the 16th percentile. So logically, the 40th percentile, Scholar, I think you see it now, the 40th percentile have to be where? And that's the 84th percentile. And, or we do percent. Logically, it has to be where? So that's the 16th percentile. Uh, 13.5 is the area between here and here. That's 13.5. This is, that's 13.5. That's 34. Those are the areas between those. I can do those again too. It might be closer to that. It's going to be somewhere around here-ish, right? That's our answer number 1. Maybe right around there. That's answer 1, right? So, but tell me this. What percentile is this and what percentile is this? So give me the percentiles right there. And here's a hint. So we're just marking the curve and practicing for the test. There's the empirical rule number. What percentiles are those? That is the what then what percentile. What percentiles are those on the curve? -2 is at the what percentile, and +2 is at the what percentile. So think about the area below -2 and the area below +2. Those are at the what then what percentiles. Not the 90. Well, that'll be between -3 and +3 is 99.7% of the area. So the question we're asking right now, what percentile is this, is what percent of area is below here? So this answer right here will be the percent of area below here. So what percentile is that on the curve right there? What percentile is that? Yep, the 2.5th percentile. Great job, Sloan, right there. That's the 2.5th percentile. So what's the one on the other side? So if this is the 2.5th percentile right here, think symmetry. If that's the 2.5th percentile, the one on the other side is the what percentile? Yep, Millen, 0.15, 2.35, 13.5. Yep, you have to break down each piece. Nice job, Millen. Millen has the numbers going on the pieces. If you go 0.15, 2.35, 13.5, 34, it's the 97.5th. Great job, Harrison, right there. That's the 97.5th. Now, Millen actually has the answer for the last one, because this is the 99.85th percentile, and then this is the 0.15th percentile right here, because if you do the 99.7 in the middle, and that's answer 1 still, then you would see right here that remainder on the outside. So that is how we can get the remaining ones. So the second question asks us, the second question asks us, where's the 90th percentile? So the 90th percentile would be between where and where? A z-score of where and where? The 90th percentile would be between a z-score of where and where? So we know where answer 1 is going to be at. The 90th percentile is going to be between a z-score of 1 and 2. So it's going to be somewhere closer to here. So my first answer, I'm just taking guesses. We're going to find the real answers here in a moment. My first answer, I'm going to say 10 or 11, 35. And then the next one, I'm going to say, and then the IQR is the range of the middle 50%. So if this is the middle 68%, the middle 50% must be shorter, must be more compact. So it's going to be less than plus or minus 1 standard deviation. So the middle 50% is going to be between there. So we should know what we're looking for graphically with the last picture where the middle 50% is shaded. Now we're going to go here to the apps and we're going to draw the answers, but we're going to see how close we got. 1135. Okay, so let's take guesses. 1135 1241. And for the last one right here, 100. Check answers. We got one right. Was it this one on the bottom? I think it was. That's the only one we got right, I think. No way. It's that big of a range? Oh, we didn't get it right. Ha. Okay. So we got one of those right. We got one question right. But let's take a look at the applets right here and actually get the real answers. Once again, we should see that our drawings basically match this. And that's the goal, is that we know what we're doing. We want to be able to say, okay, our drawing right here, this is where the first answer is at. Let's go ahead and put the mean and standard deviation in here. The mean of 1162, and then the standard deviation is 61. And then below, and we go to the 40th percentile, the answer is, and we're going to round to one decimal, or no decimals, 1147. So we're a little bit off. Glassdoor, yeah, we do Glassdoor. 1147 is the answer. So that is, we're close-ish, but not too close. Decent guess. The next one is the 90th percentile. So let's go over here and remember our picture. We said the 90th percentile is over here. So let's see where it's at. The 90th percentile is right there. And if you look at the curve where it's at 1240. I feel like oh, that's the one we got right. So that is the one we properly guessed. It is 1240. So we got that one really well. We got a guess that was correct just by doing, I want to reiterate, all we did was do the graphic, and then we took a guess and said that's about at 1240, and we said 1241, and our answer was correct just by guessing it. So for the last one right here, the middle 50% is, remember, going to be within one standard deviation. So we're going to go right here and say 50% and go between, and then we're going to subtract these two numbers because that's the IQR right there. So, oh, I know what I did wrong. Darn, it's going to be closer to 80, I think. So here's the first number minus the second number, and it's 82. So I realized what I did wrong in my head. There it is right there. And now we should have round to the nearest whole number. Uh-oh, let's see. Let's see what we did wrong. Where did I type something in incorrectly? 1162 and 61, 40th percentile. The 40th percentile is right there. Let me look at the rounding. No way is that going to be like round down or something. Don't do that. No, it's still... Okay, that looks to be correct. I think it's the IQR we have wrong now. Okay, it says the IQR is wrong. What went wrong on the IQR? The IQR. Okay, so let's look at the IQR one again. What did we do wrong? Between middle 50. And so the IQR is the range of these values. Does it say round up? It says round up, I bet, right? Wait a minute. What did I do wrong? Wow. I said it's about 80. That was like me doing it in my head. So what's the answer? I said it's about 80. What's the answer, though? Well, not quite 81. The answer is, if you take these numbers, it's 82. Well, not in million. So there's that number, Q3 minus Q1. And then I was like, oh, it's about 80. So when I was doing this, I said, oh, it's about 80, but it's actually 82. And so it was just me saying it's about 80, and then I was doing the one I guesstimated. And truthfully, it probably would give it to us. 80 was the boundary on what it would give. One thing I don't like is that a lot of these that say round to the nearest whole number, if you enter in it's giving us the answer right there. So 80 was basically right outside the range of acceptable answers. So the answer is 82, and it would have given us for 83 probably also. So it's about 80. But when I said that, apparently I didn't look at what I found in the calculator, and I put it in wrong. So there we go. That's the way it goes. Good question. Really like that one. Once again, understand how to do the drawing, and it's going to help with your understanding to be able to compute these things, and you should be able to theoretically find some of these answers on the test. So that's how I just want to double check. Yep. Make sure to not make errors like I do every once in a while. It's quite possible to make an error just putting something in. That's why you get multiple attempts, because everyone makes mistakes here at doing these sometimes. What do we got right here? Okay. Another normal model one. I think I saw Glassdoor. What was the Glassdoor one? Here we go. Glassdoor company right here. And what are they doing? Okay, the Glassdoor. Well, we got to mark the question. People are going to come back and watch this later. Okay, we are at 123.33. Stat 201. Chapter 5 quiz, part 2. The Glassdoor. Economic. Okay. So when you look at this right here, it starts off by using the empirical rule. What percent, if the normal model is applicable, would you expect to be 2 standard deviations above the mean? And we just did some drawings on this. So we could actually reverse time a little bit here, pretty far reverse time. And what percent would you expect to be 2 standard deviations above the mean using the empirical rule? So go ahead and answer this. This is totally different data, but we still are just saying, according to the empirical rule, what percent would you expect to be 2 standard deviations above the mean? This is the 68-95 rule, and this is the second number in the empirical rule, 68, 95, 99.7. So what percent would you expect to be 2 standard deviations above the mean? What percent would you expect to be 2 standard deviations above the mean? There's 2 standard deviations. There's the percent above. So once again, doing these drawings can really help. What percent would you expect to be 2 standard deviations above the mean? Don't look at their answers. 2.5 exactly, Millen, right there. Great answers. So that's according to the normal model. We would expect 2.5 out on either side. That makes this the 97.5th percentile because 2.5% is above here, 97.5% is below there. So exactly. So the answer is 2.5. Is that percent approximate for these data? Okay, let's take a look. Here's the histogram. This histogram looks mostly what? This histogram looks mostly what? Right skew, left skew, bimodal, unimodal. It looks mostly what? This histogram looks mostly unimodal, correct? Does it look symmetric? So I would say it looks mostly unimodal. That's a good way to describe it. Does it look mostly symmetric? And Harrison's right, unimodal and symmetric. So because of that, those are the 2 characteristics of normal histograms. So it looks mostly normal. That's good right there. And here is the data right here. I think they do the log of the data right here. Is it the log? They talk about log, I think, in this one. So if you notice, we see right here about 2.5% out on either side, and it looks pretty normal. Is the percent appropriate for these data? Yes, because the distribution is unimodal and fairly symmetric. Good. The answer is for no. Well, it needs to have both characteristics for yes. That's key. You can't do only unimodal because you could have data that is unimodal that looks like this. So then it wouldn't apply. That is unimodal, but not symmetric. The data is not uniform. So uniform data looks how? 4-letter word. Uniform data looks very what? Which our data, we don't want it to look uniform. If it looked uniform, it'd be like no, because the data looks uniform, this would not apply. Uniform looks very flat, so that doesn't apply. The distribution is skewed. No, it's not skewed. So these answers are just wrong right there. Now let's draw of the logged data. So they're doing the same thing right here. You don't have to worry about what logging means. Logging, if you do like a log 10 of values means you would raise it to the power of 10 to get it back. As in the log 10 of 100 is 2, because 10 raised to 2 is 100. So I think I might reverse it right there. 10 raised to the log of the value. Log transformations bring in extreme values because you could have data. This is good for the upper level classes where your data has extreme values like this. And if you go to the data logged and you go to log 10 of your data, well, now the log 10 of the data is not as extreme. So this is good when plotting your histogram, because your histogram originally is going to look all crazy. And then if you go to the histogram of the logged data, it's going to be more pulled in. So here's the regular data. It's not normal. It's very skewed. And here's the log data, which now has the values a lot closer. But we'd have to report it as logged values. So they're doing that sort of concept right here called a transformation on the data. But the only learning thing right here is, does it look normal? It actually looks a little bit more normal. Log transformations are a common transformation to bring in extreme values. We have really good notes on 320 on it. I'm not going to get into those right here, but all you're looking at is, does this look normal? And the 2 things to say if something is normal is that it is what and what, which these are the learning objectives right here. It's not about logging data. We're not learning how to log data and bring in extreme values. We're learning to see if something is normal, and the two things to check to see if it's normal are what and what. Once again, the two concepts of normality that must be present to be normal are that and this. What are the two concepts? So if the normal model applies, it'll be what and what. To properly use the normal model, unimodal and symmetric. Yep, that's it. That's all it is. So always be thinking, what am I trying to learn right here? What's the point of this question? What's it trying to teach me? It's trying to teach you that if you are going to use the normal model, you have to have unimodal symmetric data, i.e. one mode, i.e. symmetry, and other things that are skewed or uniform are not going to be a proper application of the normal model. So really great question. Just think about what are you learning? You're also talking about the empirical rule 2 with 2.5% above 2 standard deviations. Was there another one? I think we had the NFL one, right? Oh, we haven't done the NFL one lately. So, and people asked about that on Discord, I think. NFL data from. Let's go check this out. NFL data. Okay, the NFL data right here. Let's take a look at it. So here is the data. What's the first thing you notice? Immediately, what do you notice? Yeah, what do you want about, Millen? Let me know. I can check out the code and stuff. If you sent it to me on Discord, I could probably try to fix it up too. It's super skewed. So we should not apply the normal model. Like this is, if we apply the normal model right here, right skewed even, right to the high, left to the low, whatever way the monster man's tail goes, once again, this is going to be a misapplication of the normal model. So if you're thinking, should I use the normal model? The answer is no. So we can't use the whole idea of 68, 95, 99.7 because this is very, very right skewed data. So we would not use those concepts for this data. The answer is no, don't use those concepts. So taking a look right here at the data, according to the normal model, what percent of receivers would you expect to gain more than 2 standard deviations above the mean number of yards? So what's the answer? I love these questions because they're very repetitive at times, and you might even memorize the numbers. So we'll do a quick sketch right here. It said more than 2 standard deviations, but it said according to the normal. Like if the normal is true, and we go out here to 2 standard deviations, a little further out than needed, then what percent would you expect up here? What percent would you expect up there? So what is the expected percent up there? 2.5, exactly. So according to the normal model, we'd expect about 2.5%. And that's using the empirical rule right there, and 2.5%. I'm going to see if what it gives leeway on that for a moment. For these data, what does that mean? Okay, so we have here 508 receivers. So 508 receivers, 2.5% of that, no. 508 receivers times, so that's about 13, round to the nearest whole numbers. 13 receivers, so I just did 2.5% of the 508 receivers. And then we're going to go right here and go to the mean. And the mean is 253.763. And what do you think we're going to do to it? Because we're going to find the value here. We're going to go to the mean and find where this is at. Because we need to go to the mean and add what? We need to go to the mean and add what? Because we're no longer doing the z-score here. We need to go to the mean and add what? How are we going to find this answer? This would mean for this data, we would go to the mean and we would add what? To find the answer for where we're at on the curve. We would go to the mean and add what? How many times? Exactly. We'd go to the mean and we would add 2 standard deviations. This is different data, but the concept still applies, that it's saying, well, where is this point that is 2 standard deviations above the mean? So we're not going to add 2, though. We're going to add 2, and I think Skylar might be saying that right there. Good answer, Skylar and Millen right there. We're going to go to the mean and add 2 standard deviations. So we're going to go to the mean and go plus a standard deviation plus a standard deviation. So it says right here that this is the mean of the data, and the standard deviation is this right here. And then we're going to add it. Whoa. Really? 253.763 plus 312.335359. There we go. That's 2 standard deviations. Round to the nearest whole number. Doesn't say round up. There we go. Explain the problem in using the normal mod here. It's right skewed. Boom. That should do it. Yes. Let me look at the leeway on this. Does it accept 2.4? No, it doesn't. It is using the empirical rule right there. 1 decimal. So be very careful. It is using the empirical rule. Yes, Doc, good question. You are going to have to know how to do it by hand. So here we'll do another one right here in the middle, and let's do your question. So if you look at a question like this right here, use the normal model. We'll do this one right here, and watch how we can kind of do this. So I am not going to use the applet for this question. Are you ready? So let's label this how you would do the questions on the test. So this question, I'm going to label this part of the video, Stat 201, Chapter 5, how tests will look. And then I'll put the thing right there, use the normal model. Okay. So if you look at this question right here, I can solve a lot of these pretty decently, I think, using my knowledge of how the normal curve works. So with this one right here, I'm going to go down and go to minus 24. So I'm going to go to 71. The IQ of the 94th percentile, that is going to be around, oh man, it's a tough one. I'm going to go to 1.6. So 1.6 is, would that be right? Yeah, 1.6-ish. That's going to be around, I'm going to explain what I'm doing here in a second, but I'm trying to solve these quickly in my head. 32. So 32 is going to be 127. And for the last one right here, round to 1 decimal, that's going to be about 30.2. Let's see how I did. I got 0. Okay, so these were my guesses. These were my guesses. So if you were doing this on the test, what would you do? What would you do? It wants to 1 decimal, so that's a hard thing to guess. But what would you do if you had something like this on the test and you, maybe it's multiple choice, like it has multiple choice answers, draw it out. So we're always going to draw it out first. And let's go grab the info right here and start drawing on this. So with this right here, we take the numbers and we start drawing on the curve. So here we go. We put it here at the center, 95. We go down by 20 each time. That's just the standard deviations on a normally distributed curve with 95 at the center and 20 as the standard deviation. We go up by 20. And then we put the z-scores below here. Always put your z-scores. And what I would know is I would know that the 11th percentile, and we did this earlier, so check out an earlier question where we labeled all the percentiles. You know what we might be able to do? Can we? Can we? No, we can't. It's selecting all of it when I select that one. That's such a bummer. I wanted to just select these right here, but it's going to select all of those. So we could label these percentages. Check out earlier where we did it. We would just be kind of repeating the process. But these values can be found right here using the empirical rule. Check out earlier where we did it all by hand. So, oh, that's not correct. It's the 99.85th percentile right there. So the 11th percentile has to be somewhere in here. So that's answer 1. So if you notice, I went between 55 and 75 with my guess. And it's probably a little bit lower. We'll see in a moment. And then the 94th percentile has to be over here somewhere. That's answer 2. And then the middle 50% has to be between here and here. So we'll see how close my guesses were, but that's where the middle 50% is. And this is how we do it. You're welcome, Harrison. Good work. So that is how we would draw it out and be able to take educated guesses. Now we're going to go here and draw it on the curve. And the 11th percentile means 11% is below it. And if you take a look at this right here, 70.5. How close was I in my guess? I said 71. The right answer is 70.5. So we were super close. The right answer is 70.5. The next one is the 94th percentile. And the 94th percentile means 94% is below that point. So we'd go right here and go 94% below. It's 126.1. And look at that. I was less than 1 off. And so I was very close on that guess. Once again, it's hard to guess to 1 decimal. And then the middle 50% is between here. And we need to subtract these numbers. So let's take the numbers and subtract them. And there we go. It's 20. It's 27. Oh, I was further off on that one. It's really 27? I guess it is. I guess it is. So that was the one I was the furthest off on, but decently. We did pretty well on it. Remember, these are the real answers, so let's compare. These were our guesses, just using that's the real answers, and then here are our guesses, really. So 30.2, I think it was 127 was our guess, and 71 was our guess. So there's Brian's guesses versus the real answers, and if you notice how close we were able to get, pretty close, just guessing it using our knowledge. Some of them are more difficult, but once again, what we did is we drew it on the curve right here, and we said, where would the answers be? Because if this is the 84th percentile, and we're looking for the 90th, 94th, it has to be between here and here. We were looking for the 11th percentile. It has to be between the 2.5th and 16th. So questions on the test could give you multiple choice. They could give you pictures to use, but there's lots of ways we can do it where you can have a very good educated guess at the answers. There's one of these that I really like that I can usually guess that says round to 1 decimal. That's not the round. Well, that one of them says round to the nearest whole number. I did it earlier and I did pretty well on it. I think those are fun. Oh, is it this one right here? We've already done. Round to the nearest whole number. Okay. So it says 40th right there. I'm going to try to do this one. The Millen, we'll take a look at your work right here. Round to the nearest whole number. Okay. So is it going to change the problem? No. Okay. So this is question 11. We'll do one more version of this right here and then we'll... Question 11. Okay. So let's see. Can I do this problem? The 54th percentile is a little bit above the mean. So I know that we should go just a little bit above the mean with this answer. So 54th percentile, maybe 10 above the mean. So 1154, because it's not quite 1 standard deviation above the mean. It's just a little bit. Matthew, you might have to message me or send pictures. Message me or send pictures. I'll probably take a look at that. 91st percentile is somewhere between the 1st and 2nd standard deviation. It's probably right about in between. So if it's right about in between, it's going to be about 90 above. So it's going to be about... Then the IQR is basically 1 1/3. A little bit less than that, right? Well, so about 1 1/3, so 120. Got 0. I'd have been close on some of these. No. Well, darn. Now let's get the right answers. Okay, so the mean on the curve is 1144. Standard deviation is 63. We want the 54th percentile, so below. And, oops, round to 0 decimals. No, go away decimals. 150. Really? That close? Well, B. I said it was close, but I didn't know it was that close. The 91st is 1228. That's a tougher one to guess. And then the IQR is the middle 50%. Between, and we subtract these 2 numbers right here because that's Q3 and Q1. So there we go. 85. What am I doing on my IQRs? Oh, I really did. Oh, I think I did 90. Oh, gosh. That's what I'm doing. Okay. So we are able to solve it pretty quickly. And once again, decent guesses. Really bad guesses on the last one. But the better you get at these, the more your knowledge increases, the more you can take educated guesses and understanding what the curve is showing you. So I'm going to try one more attempt. And Millen, have you sent me the work right there? We'll end with that probably. The 35th, ooh, no, it's kind of between 90th. Oh, I can cheat and do that one. The 90th percentile, I actually know the z-score for. It's 1.2816. And if I times that by 99, and add that to 1181, then the answer is 1308. I know that answer. 35th percentile, that's a very hard one to find. It's probably about 50 below. So I don't know. We're taking a guess at that one. And then the IQR, this time I'm going to get it right. This time I'm going to put in 133 or 132. And let's see how many we got right. 66%. It's probably this one right here because that's the hardest one to get because it's in such a small area. Yeah, so it is this one right here. It's going to be around there somewhere. I don't exactly know where. Once again, we can use the applet to find the right answer. But as we can show, we can take decent guesses at these if we know what the curve looks like. And I've done too many of these. I've done way too many. So it's 1143. There we go. That's got it. So there's another version. Once again, I'm only using the applet at the end of this to check my work with my knowledge of how the curve works. Once again, this is right above the mean. So let's go 1140. This is between 1 and 2 standard deviations. So let's go about 1 and 0.3 standard deviations. So maybe 110 above it. 110, yeah. Round up a little bit. So 112, 45. And then the IQR is about 1, 2. How do we do on this one? 33%. So we are getting some correct. Yeah. Oh, I wish I was good at GeoGuessr. I'm probably horrible at GeoGuessr. People look and they're like, oh, that looks like a Spanish cottage or something. And I watched some GeoGuessr stuff. It's pretty interesting to see what people can do. Just the better you get at guessing these. If I had to say, we probably got the 53rd percentile correct. Yeah, we did. We got that one correct. That was the one I thought I might be best on. This one's a lot tougher right here. That's why I was like, I don't know. Well, give a little leeway around it. Yeah, but once again, just go to the applet, find the right answer here. On the applet, put in your mean or standard deviation, and then standard deviation of 89, and then the 53rd percentile. The actual answer for that is this, and we were very, very close in our guess. And then the next one is the 91st percentile, which is between 1 and 2 standard deviations, 1251, really close on the guess right there. And then the last one we should be super close on. Really? There it is, which we can just find. But once again, this is a great question. I think this is probably one of the best questions. And if you know how to solve it, you understand what you're looking at with percentiles. Percentile means area below a point. So when you're graphing these, you have to think about what percentile am I at on the curve. And we've got the percentiles listed there. Really good to just understand percentiles to this degree. But good stuff right there. Let me see, Millen, did you send the question? Let's take a look at the question. This is how my graphs look, but it doesn't look good since it's hard to read the graph, so I'm confused. Okay. You've got an extreme outlier. It's a very weak relationship. I would switch your X and your Y. Switch the X and the Y because you're probably trying to see if white's rating explains how many turns it takes. So it looks like there's a positive relationship, but there's also an extreme outlier. So you might want to go with, but there's also a ton of data points. So with lots of data points, one data point might not influence it that much, but it might be worth, you definitely want to mention that extreme outlier, that it took a ton of turns. And that one point is probably making the relationship more positive. You might go with Spearman still. Is this making sense right here? And then this is what it shows in our shows. We're going to run it. You might have to send me all your code. Like, send me all your code. So, and then you want to make sure the plots look good when you take the screenshot. I think you will. Like, you're just saying quick screenshots now. Yeah, because would you think it makes more sense to say someone's rating explains how many turns it takes? Does that make sense? Like, the X variable is the explanatory. So somebody's rating explains how many turns it takes to play. So the rating somebody has, you know what you could also do? Millen, you know what'd be really cool? I'll show you a really cool thing. Let's look at this. Go to your data set and do the following code and tell me what I'm creating right here. Is that not it? Oh, we don't have the chess quant data set. Maybe I deleted it. Okay. So I want you to think of what this means. You ready? what does a positive number mean right here? What does a positive number mean right here? What does a positive number mean? So this, I would suggest doing this code right here and thinking about what this means then, because you've created a variable here. What does it mean if this number, or not positive, what does the number mean if this number is 1 or greater than 1? What does it mean? I did chess quant white rating divided by chess quant black rating. What does this number mean? Like, what's the context of this? Which is very interesting. Yes, if it's greater than 1, then white had the higher rating, right? So it's like the ratio of white to black, right? So let's go here to chess quant white ratio, or we'll put W ratio. We could do it either which way.
It doesn't matter.
So that is the ratio, right? And I bet you, I'll do this right. So let me just do it really quickly. Make this graphic look pretty, but I would bet, I'm doing this a totally different way. I would bet the ratio explains how many turns it takes. So turns is just right here, right? Turns, I would bet the ratio totally explains the turns to a certain extent. Turns not found. How is turns spelled? Do I say turns? Oh, it's lowercase turns. Okay. Ooh, yeah. So there's a lot of variation right here, but there's a what relationship very clearly, which is what I expected. There's a lot of variation right here, and this is not a pretty graphic yet. There's a lot of variation, but there's a what relationship right here. We could do the association on it too. There's a what relationship right here. Very clearly a what relationship. Hey, Nick, have a good one. Very clearly a what relationship. Yes, I'm gonna run it. Very clear. Ooh, look at these outliers. Oof, look at those outliers. But still, there is a what relationship, and we'll look at the, there it is right here. I mean, it's partially due to outliers. There's lots of outliers, and it's interesting. And look at the heteroscedasticity is the most variation is when they're evenly ranked. That's, Millen, this is what's really interesting about this. The most variation in the data on how long it takes to play games. So we didn't really find good correlation right here because the correlation is weak. It is negative, as in the higher the ratio, the less turns it takes. There's a negative relationship between higher ratio of a player to someone else, and then it takes less turns, as we would expect. If you're better at chess, it would take less turns. And also we see less observations over here because usually people aren't going to play people with such a bigger ratio than them, because you'd have to be really bad or really great, and you're probably not going to then play each other. You might be like, well, why would I play you if you're 3 times better than me? But also the most variation in how long it takes is when people are evenly matched. And then also over here, we see that it might be, if we fit the bendy line, well, it might, you know what it is? Millen, I bet you this is a non-monotonic, because I bet you it takes less turns down here, it rises, and then it takes less turns over there. So, and yeah, I bet you that's it. So now we need to go back to our plots, and I bet you there is a non-monotonic relationship, which is what we'd want to mention right here. This is what we're learning. Yeah, exactly. So it wouldn't be monotonic. This is the whole goal of what we're doing. So we're just going to take, yeah, this is, oh man, can't tell I love doing data. It's a lot of fun. It's like, okay, so that's probably why this is looking this way. What the ratio, W ratio. So we are going to look to see if the ratio explains the turns. We're going to use the LOS method right here. We're going to do Spearman because we're using LOS. And then, I think that's got it. Ratio correlation between, so Spearman, R between correlation, why not? Between turns and ratio. I think that did it. Oh no, okay, SP2. No, that's not the graphic we want. Okay, Okay, it is working now. What did I not run? I didn't run something, right? I didn't change the variables. I think I have now, and it's taking a while to run. So with a lot of data, these things can take a while to run. So you have to be, so I don't know where I put the labels. Ooh, see, there's our label way out here. So the label's going to have to be in here at about, 2 or something, right? So that's the bummer is if you make a graphic and then you've done something crazy, then your graphic's going to take a little bit of while to reconfigure. Yeah, it's a pretty cool data set. And we should probably see the non-monotonic relationship now. Even if the label's not perfect, we're really just looking at to talk about and say, well, this is non-monotonic. And we'll probably see the upward. Yeah, look at this. There it is right there. We even called this Millen to say that there's probably some sort of non-monotonic. And this is where we would say that this isn't properly described by a Pearson or Spearman. That's why both correlations are turning back very small numbers. We might talk about the greatest variation when people are evenly ranked. And we would take the label and put it up here around 250. So that's how I would explain this. So is this making sense, Millen? Like, you're not meant to find the most amazing things ever. You're meant to interpret and explain and know what's going on with this and know why. You're meant to understand why Pearson and Spearman would be wrong for this data. And it actually goes to the understanding of the data that when games generally take longer, oh man, it's almost in the perfect spot. 1.5. I wish you could just move the title. I wish you could just like grab it and move it over. Plots aren't that perfectly. So it's not well described by either correlation. The point is not, the point is not to find correlation. The point is to know how to properly use correlation. So you're not meant to find things. You're not meant to be like, I found something that changes the world. And you know what's interesting? This correlation is what? It's right behind my head now. Even though this Spearman correlation is small, it is what? Even though this Spearman correlation is small, it is still what? Even though this Spearman correlation is small, it is still what? It is still statistically significant. But here's the thing. It's probably, or it is basically, no worries. It's because we have so much data. With so much data, we can sometimes find things that are statistically significant with low values, but this has no practical significance. Like, although this is, and great job, Jesse, right there, it is statistically significant. The p-value is below 0.05. And you might say, but this looks like a random blob. And well, it's because it's 200, whatever crazy amount of data points. We have so much data that we actually found something statistically significant that is not practically significant. Also, it's not going to be well described by Spearman or Pearson because there's outliers, it's heteroscedastic, and for Spearman, it's non-monotonic. So there's lots of problems right here. And this is what you want to get into with your data. Like, that is the deeper understanding. You're not being graded on finding correlation. You're being graded on interpreting and understanding how to properly use correlation. So it's not like, oh, you found a good correlation, good job. It's, okay, how does your data work with these concepts? And there's probably other ways to do this. Like, there's other things we could do with this data. There's a lot more variables to use. But at this point, there wouldn't be a really good correlation right here, Spearman or Pearson, for the ratio of these variables. So how does that look, Millen? Does that make sense? You're never meant to find things in these reports. It's cool if you find stuff, but you're meant to use the concepts we learn throughout the week to properly interpret data. That's the whole point of every report you do, is to, like, can you apply the concepts that you are learning to a data set? Like, if you were to go work for a company, you could be like, oh yeah, I learned how to do this. Oh, well, there's really not any good correlation right here because it's a non-monotonic relationship. So, with Pearson, we need a line. Well, lines have to go in one direction. So the idea of it being non-monotonic, well, a line can't bend. So this is not well described by a line, nor is it well described by a monotonic relationship. Although there is statistical significance, there is no practical significance in this because the Spearman correlation is just about zero. It's pretty much zero. For all intents and purposes, zero. Yeah, you could. How many, and opening moves means what? Like if they're using like a certain set of, like, there's names for the moves, like Queen's Gambit or whatever. I don't know what that is. There's certain names for things. So maybe it's like if you use a certain opening move and how many, it's a starting move. Okay, so yeah, if you do a certain like move thing, then how many moves are in that opening move? And maybe that might explain something. But here's the thing. Remember, you're just trying to make graphics and interpret them. So you might find something cool. You know what would be interesting too? Maybe people with higher ratings have more opening moves. How many will lead to turns? So you could look at, people, you can do different things with this. Let me know if you have more questions, but you should have enough variables now to run through the analytics. And Google Drive wants to start up. Not now, Google Drive. But until then, bye for now, everyone. Bye.